Hello students, welcome to the class. So today we'll see the theory part 12 of the chapter 6 equilibrium, in which we will be covering section number 6.13. So this is the disclaimer. Now in this class our objective would be to look at the solubility product constant. So this is a new term which will be referred to a certain species. We will know about it. So let's start our class. Now, if I talk about the specific sections of the NCERT that we are going to cover, so though that will be the 6.13, as already mentioned, whose name will be solubility equilibria of sparingly soluble salts, in which we will cover the 6.13.1, which is solubility product constant. After that, we will do a NCERT problem 6.26 related to this same topic. Now, to understand this solubility product, first you should be aware about what is solubility. So we will try to define this solubility in terms of ionic salts. Okay. So solubility means the maximum amount of solute that can be dissolved in a given solvent, and that should be given at a specified temperature. All of this is done to make a saturated solution. Now this definition that you are seeing is specific to all of the type of solution, but still we are studying about ionic salts, so we will keep our discussion to this definition according to ionic salts. So what can you understand from this definition? I hope this is crystal clear. So it is the maximum amount of solute that can be dissolved in a given solvent. The important part is the temperature part, right? Because you know that solubility is something which is quite related to temperature, because processes are endothermic and exothermic, and most of the cases solubility is the endothermic process. So it may change, or the amount of solute may change depending on the temperature. So you should fix the temperature first of all, and once you make a saturated solution, the amount of solute that you have dissolved in a given solvent will be called as solubility. Its unit is gram per 100 ml. So basically you are taking 100 ml of solvent and you are calculating the amount of solute in terms of gram, right? So this is your unit for the solubility. But you will mostly see this molar solubility in your numerical problems, because in terms of molar things, your calculation becomes quite easier. Now, what is molar solubility? So basically, it is the moles of solute which can be dissolved in 1 liter of a saturated solution. Again, if you look at the aspects of this given definition, then the parameters are changing for the solute and solvent amount. Like now you are giving the solute amount in terms of moles, and you are giving the solution amount in terms of liter, and that should be precisely 1 liter. Coming on to the unit, so of course moles has a unit of mol, mole, and liter has a unit of volume as a unit of liter, so that will be mole per liter, right? Now, what are the factors that affect this solubility? So, we will look on those factors, and hopefully there will be a part of thermodynamics as well. But the most important part would be your common ion. You will see that. So, what are the factors? Starting from temperature, then we have this lattice enthalpy, solvation enthalpy, okay, and lastly, our nature of solvent. So, we will study these 4 factors today, right? And what about this common ion? We will look at that in the next class. So that is a different topic to discuss. First, we will try to see some general parameters, which is obvious, right? So starting from the temperature. Talking about the temperature, we know it very well that the solubility depends upon temperature. Now, hopefully this part is clear to you, because you must have seen that if you are, suppose you are taking a liquid, suppose water, and you are trying to dissolve salt in it, you will put salt as much as possible. After a certain amount of time, this salt will get deposited in the bottom of the container. But if you start heating that same solution, you will notice that the precipitated, or the I would say the settled down salt in the bottom start to dissolve further, right? So from there also, this is a very short experiment. From there, you can quickly say that, okay, there is a very strong relevance of temperature for your third for your dissolution of salt into water. Now, most of the solid salts become more soluble at temperature increases. So this salt solution would be a classic example for this given statement, and it is seen in most of the cases as well. So what you can say that solubility is a kind of endothermic process. Moving on to the next parameter, we have lattice enthalpy. What is lattice enthalpy? We have talked about this. So this is the energy that is required to completely separate 1 mole of solid ionic compound into its constituent gaseous ions. Suppose you are taking sodium chloride in solid form, then you are applying energy on it to break it into sodium plus gaseous and Cl minus gaseous. I would say sodium cation and chloride anion. Now, those will be present in the gaseous amount. The energy that is put upon to do this process is called as the lattice enthalpy. So, if you are talking about energy that is being given to break the ionic salt, means lower is the energy, easier it is to break that salt, right? So we can put up a direct link here. What is the direct link? That if you are having a higher lattice enthalpy, that means you will need more amount of energy to dissolve your ionic solid, therefore resulting in a lower solubility. So we can say that lattice enthalpy and solubility are inversely proportional to each other, right? Is it correct? So this is a very general thing. You can just think about it, and I hope you can easily analyze this situation. Moving on to the next factor, we have the solvation enthalpy. Now, what is solvation enthalpy? Whenever you are dissolving 1 mole of a solute in a given solvent, then the enthalpy change accompanying that process will be called as what? Solvation enthalpy. Remember, you have to take a situation where your solute is being dissolved in an infinite amount of solvent compared to the amount of solute that you have taken. So, basically, you are taking a case of infinite dilution, and your pressure should also be constant. So, this is your solvation enthalpy. And in most of the cases, it is seen that it releases energy. This process releases energy, solvation. Now, if it is releasing energy, that means the energy will have a negative value, and more energy your ionic solid releases on the solvation, it is easier for your ionic solid to get dissolved into the solvent. Now you have two thermodynamic parameters, I would say. First is lattice enthalpy, which is inversely proportional to your solubility, and the next is solvation enthalpy, which is directly proportional to your solubility because it helps us in releasing energy, or you can say this process is something which is making the system more stable. So they are opposite to each other. Now, what is the relation between this? How we can decide with the help of these two thermodynamic parameters that our given ionic solid is soluble or not? We will look on to that. Before that, let us look on the fourth parameter, which is nature of solvent. So it is very, very important to understand this part also. Now, if you are considering a ionic solid, you must be getting an idea that non-polar solvent will show less solvation energy, or you would say it will show less solubility. Now, what is the reason behind it? Because your ionic solid would be better stabilized if your given solvent is having a charged environment. I would not say the environment is completely charged. Overall, it is neutral. But inside the bulk, there would be a situation of partial negative and partial positive character. But if your non-polar solvent is there, then in that case, that interaction would not be possible. And due to this no interaction situation, we will see that the ionic solid are less soluble in non-polar solvent. Now, why are we saying that this interaction is important? Because if you are trying to dissolve a ionic solid into a non-polar solvent, these interactions were important because these interactions are kind of what? Attraction type of force. Because positive and negative will attract each other. But if your solvent is non-polar, that means there will be no positive and negative part of the solvent molecule. Therefore, no interaction, or I would say no attraction, therefore less stability. And if the solvation energy is less, means less amount of energy is released during the process, that means your ionic solid will not be soluble in your non-polar solvent due to the insufficient amount of energy released during the solvation process. Then we can put a general statement here that salts are generally insoluble in non-polar solvent. What about the polar solvent? So it's very obvious they will have a high solvation enthalpy, and the reason is the strong interaction of the solute through electrostatic force with the solvent molecule. Consider you are taking the water molecule, it has a positive and a negative part, like hydrogen is going to the positive part and oxygen is going to the negative part. So each part will do a corresponding interaction with its negative part of the solute, right? And that will result in a strong electrostatic force of attraction, resulting in lower energy, because attraction forces always results in lower energy and repulsion forces always results in higher energy. So that is the basic nature of the energy. Now, if there is a stronger interaction and your system is going to a stable state, that means energy will be released and that energy will be enough to break the crystal lattice, or you can say to overcome the crystal lattice energy, means your solvation energy is enough to overcome the crystal lattice energy. So what can you conclude from these 2 points? That salt dissolves in ionic solvent, interaction overcome the lattice enthalpy, right? So when your ion solvent interaction overcome the lattice enthalpy, we can see a complete dissolution of the salt. So this is your thing. And this is seen better in terms of polar solvents and poor in terms of non-polar solvents. Now let us move on to the characterization of salt. We have seen what are the things that affects the solubility of a given salt. Now we will try to define a way to characterize the given salt. On what basis we are characterizing it? We are characterizing them on the basis of their solubility, that how much amount is being able to be dissolved in the given solvent. On that basis, we have 3 categories. We have category 1, where the salt is highly soluble and solubility is greater than 0.1 molar. Now coming on to this 0.1 molar, so this is basically the molarity of your salt, which is possible for your highly soluble salt. Then, talking about slightly soluble salt, their molarity lies between 0.01 and 0.1. So in between their solubility lies, we can take the example of calcium sulfate, silver chloride, and lead chloride, right? And the third category, which is in our interest, which is sparingly soluble salt. So this is the part that we are going to discuss. Now, we will discuss this sparingly soluble salt in terms of solubility constant, right? We have said that we are going to clear this objective, and this objective will be objectified to this sparingly soluble case. Here your solubility is very, very less. It is less than 0.01 molar, and we have example of lead sulfate, barium sulfate, and your iron chromate. So let's start with this sparingly soluble salt. So I said that we will talk about this solubility product constant in terms of sparingly soluble salt, and here is your quantification. What does that quantification says? First of all, we know that your sparingly soluble salts are soluble in to a very small extent in a given solvent. As a result, the concentration of the dissolved ions, because if salt is dissolving, that is for sure that it will break down into ions, right? Remember, no matter what kind of salt you are taking, it will, if it is soluble, it will be dissociating 100%, up to 100%, approximately 100%. And in numerical sense, we can take it equals to 100%, right? So whether you are taking sparingly soluble salt or slightly soluble salt or soluble salt, they will always, if they are soluble, they will always be completely dissociated in the solvent. That is for sure. They are always considered as strong electrolyte, right? Suppose we are taking the example of barium sulfate to understand this KSP. So this KSP is basically the symbol which is used for the solubility product constant. And how do we define it? It's very simple. First, let us take the dissolution of barium sulfate into the solution, producing the barium 2 plus and the sulfate 2 minus. Then, if you are calculating the equilibrium constant for the above reaction, that will be written as Kc is equals to concentration of the barium 2 plus multiplied by the concentration of sulfate divided by the concentration of barium sulfate, right? Further, if you are trying to define the solubility product constant, it's very simple. You will simply take the concentration of the dissolved ion in the saturated solution. What else is left? Your excess amount of barium sulfate is left, right? And remember to raise the concentration of this ionic species by the stoichiometric coefficient. Here we are not doing it so because already it is raised to the power 1. We don't need to show it, I will say. Now, from the definition of this KSP that we have seen just now, we can say that it will be Kc multiplied by BaSO4 concentration. Why we are saying it? Because this multiplication of Ba2 plus and SO4 2 minus concentration is equals to this Kc and BaSO4 concentration. Therefore, finally we can write that KSP is nothing but the concentration of barium 2 plus multiplied with the concentration of sulfate, each raised to the power of this stoichiometric coefficient. In this case, it is 1. Now, what about the relation between the solubility? We said the start about the solubility that it is the maximum amount of salt, which I would say the solute, which is soluble in the given solvent. Now, how we will develop a relation between KSP and S? Let's see. For that, we are considering that a solubility of your barium sulfate is S. Further, in a saturated solution, we know that the Ba2 plus concentration will be S because S is considered as solubility. Therefore, at saturated solution, we know it very well that the concentration becomes equals to the solubility. So, sulfate ion concentration is equals to S, as well as the barium 2 plus concentration is equals to capital S. Next, we know that what is KSP? KSP is equals to the concentration of barium 2 plus multiplied with the concentration of sulfate ion. Further, if we substitute the values of this ionic species concentration, we will get it as S square. So, S multiplied by S, that will give you S square. Or we can write it as S is equals to root under KSP. So, this is your relation between KSP and S. Now, one thing is very, very important. Why are we saying that at equilibrium, we are taking the concentration of Ba2 plus as S? You must think about this situation. See, I said that KSP is equals to barium ion concentration and sulfate ion concentration. And then I substituted instead of this concentration term as S. Why I am saying it? Because S is what? It is the maximum solubility. And when you see the maximum solubility, you see it at equilibrium. Because after equilibrium, there is no change. Therefore, we can take this S solubility as the concentration of the ions at the equilibrium as well. Got it? Now we will try to define this same relation for a general case. So this would be more important to you. Let's see. So we are considering a sparingly soluble salt here, and that sparingly soluble salt is being represented as MXXY with P plus as charge on M and Q minus as charge on X. Remember this is very important. We will use this part. Next, if I ask you what is the charge due to M, then you would say that, okay, X amount of M is present and on each there is a P plus charge. Therefore, the total charge on M will be, due to M will be X into P plus. What about the charge due to X? So that would be Y into Q minus, right? Now, overall, we know that this salt is neutral because salt is neutral, right? So we take the salt in such a way, such a stoichiometric way that its charge is completely balanced by the cation and anion. So can we say that xp plus is equals to yq minus? Absolutely. So for neutrality, we can say that xp plus is equals to y into q minus. Further, if you want to show the equilibrium condition where your salt is present in saturated solution, so you can write it as mxxy has a solubility of S, right? Sorry, has a state of solid, right? And that will be producing X moles of M, Mp plus and Y moles of Xq minus. So these are ionic species. So these are ions of M and X, and they will be present as aqueous form. Further, if you want to define the KSP, then what will be the definition? We know that it is very simple. We have to write the concentration of each ion and we have to raise them, which is to a power which is equals to the stoichiometric coefficient. So we can write it as Ksp is equals to Mp plus raised to the power x and xq minus raised to the power y. So this is your final calculation for Ksp for a general case. I hope you are getting my point. We'll try to apply it on a complex situation as well so that you can get a clear idea. First, we'll try to develop a relationship like our S and Ksp in the barium sulfate. We will develop a relationship here also. So what we can say for general case, if S is the solubility of Mp plus and Xq minus, then further the total concentration of Mp plus will be X into S. So this is very important to understand. So we are saying that the concentration of Mp plus is S. Then if you want to find the total amount of Mp plus, then you have to multiply it with the X, because we know that S is what? It is the amount which is present in a given per liter of solution. But if you want to define, if you want to know that how many moles of Mp plus are there, then from the equilibrium reaction, we know that X into Mp plus are there. So therefore, we will multiply this. In place of Mp plus, we will take it as S and multiply it with the X into S. Similarly, for Xq minus, we have Y into S. Further, on putting the values for both of this in the Ksp equation, what we will get? We will get it as Ksp is equal to X multiplied by S raised to the power X and Y multiplied by S raised to the power Y. So this is your most important equation. Now, since the base are same for S raised to the power X and S raised to the power Y, we can just add the powers. So X plus Y, and that is going to the power of S. What about X and Y? If you just open this bracket, this small x will go on to X as well as S. Similarly, for the Ys term, if you open the bracket, the Y will go on to Y as well as capital S. Further, we got the complete formula as Ksp is equals to X raised to the power X, Y raised to the power Y, and capital S raised to the power X plus Y. We can just solve this equation in terms of S raised to the power X plus Y also. So that will be giving you S raised to the power X plus Y is equals to Ksp divided by X raised to the power X multiplied by Y raised to the power Y. Or you can just transfer this power onto the right hand side. Okay. And that will give you your final equation, which is equation 6.45. And here we are seeing that S is equals to Ksp by, in the denominator we have X raised to the power X multiplied by Y raised to the power Y. And this whole thing is having a power of 1 divided by X plus Y. So in the denominator we have X plus Y, in the numerator we have 1. So this is the overall power. Now this is the most important equation from where we have the maximum chance of getting questions. Now what we will do, we will apply this formula onto a complex salt. Now try to remember this or note it down. So moving on to an example which is Zr3, then PO4 race having a coefficient of 4, right? Further, if I show the dissociation here, then this whole thing will be going to 3 moles of Zr4 plus and 4 moles of phosphate ion. Then further I compare this given equation with our general reaction. What we will see in this, that instead of M we have zirconium, and instead of X, capital X I would say, we have the phosphate. Now what about X and Y value? Just compare this equation, you will easily see that X has a value of 3. And what about Y? Y has a value of 4. So here you can you must be having a confusion that which 4. So we have a PO4, and outside the bracket we again have a 4. So we'll take the term which is outside the bracket of the PO4. Now using the equation 6.45, we know that capital S is equals to KSP by X to the power X multiplied by Y to the power Y, and whole is raised to the power 1 by X plus Y. If you put the value of X and Y for the zirconium salt here, then you will get it as KSP by 3 raised to the power 3 multiplied by 4 raised to the power 4, and whole thing is raised to the power 1 by 4 plus 3. Now this will be equals to 1 by 7 power, and the base is KSP by 6912. I hope you are getting the point. Now you can try this same formula for BaCl2. So this would be a homework for you. Just try it by yourself, and as soon as you see a salt, try to apply this formula, right? I hope you are getting my point. So this formula is very, very important. Two formulas are important. Before that, we got a relation for KSP and the ionic concentration. But this one is most important. Questions are most probably asked from this given equation. Now we will move on to solubility quotient. To get a small idea of this solubility quotient, you can relate this term to the reaction quotient, right? So whenever you apply this reaction quotient thing onto a sparingly soluble salt, you call it as a soluble quotient. You will see this, there is a greater relevance here for both of them. So it is basically the same formula that we are using here, only the situation is different. Here we are not using the equilibrium situation, right? But you will use the same formula which we use for the KSP. So if you will define it for QSP, it will become QSP is equals to MP plus raised to the power X and XQ minus raised to the power Y. Here, the concentrations that you are seeing for M and X are not at equilibrium. They are at any condition. So they can be at equilibrium or not at equilibrium. So all conditions are applicable here. Now, if we consider all the conditions, then there can be 3 cases for it. And that will help us to predict the state of reaction or the solution. What are those 3 states? So the first case is that your KSP is greater than QSP. So you consider your salt, you dissolve your salt, and then you try to calculate the QSP, and you saw that your KSP value is greater than your KSP value. That means you are having a unsaturated solution. Means you can dissolve more and more salt. Second case, if your QSP is greater, that means you have dissolved, you have already dissolved an inadequate amount of salt into the solution, an excess amount of salt in the solution. So that in that case, we will call your solution as supersaturated, and in that case, you will see a precipitation where your salt is coming out of the solution. Third case, where KSP and KSP are equal, so that would be the case for equilibrium. In that case, you will not see precipitation, neither your dissolution. So the rate of dissolution is equal to the rate of precipitation. So this is the third situation. I hope you are getting my point. Now we will do a question. Remember the formula. I hope you have noted this formula in your copy. So let's see how we can solve it. So the question is saying that the solubility of A2X3, so there is a general formula, a hypothetical salt is given, and it is dissolved in pure water. Now you are saying that neither kind of ions react with water. So this is the next assumption that we are taking. Okay. Now in that case, you have to decide that what is the solubility product of A2X3. Okay. No, you have to calculate the solubility. Solubility product is given. It is 1.1 into 10 to the power minus 23. How we'll solve it? Let's see. First of all, we will note down what are the things that are already given. We have the KSP value 1.1 into 10 to the power minus 23. Then, if you want to calculate the solubility product KSP, then it will be for A2X3, the dissolution will look like 2A3 plus and 3X2 minus. So, we have 2 as a coefficient of A and 3 as a coefficient of X in the given formula. As a result, we will get 2 moles of A3 plus and 3 moles of X2 minus. What about charge? How we are deciding the charge? It's very easy. Whatever is the coefficient of X, that will become the power as a charge of A. And you can take 3 positive here. So why are we saying that A must be the positively charged species? Because here we are taking the conventional case, because in most of the cases, the cation is written first. Whenever you see a formula, you see the cation is written first. Therefore, we have taken A as the cation here and X as the anion here. Further, if we use the equation, NCERT equation 6.44, then KSP can be given as A3 plus raised to the power 2, X2 minus raised to the power 3. Now next, we calculated the KSP, but the problem is that we need to calculate the S and we don't know their individual concentration, but we know it very well that at KSP, your solubility becomes equals to the concentration at equilibrium, and KSP value is already given. Further, what we will do, we will calculate solubility. How we will do it? So, suppose S is the solubility of the salt A2X3, then A3 plus concentration will be 2S and X2 minus concentration will be 3S. So, that is directly coming from the stoichiometric value of this A. See, we have a 2 here in the subscript of A. So, we are writing it as 2S. Remember, we have done this same thing in the case of general case. Okay, here the task for you. You can apply that same general formula to solve this problem as well. Here we are doing it through a longer method so that you can see the things happening one more time, because this thing is somewhat mischievous to understand. It creates confusion. So you must know the derivation as well. For that case, I am giving you the derivation as well. Further, on putting the values, what we will get? The KSP will be 2S square. So that is very clear, because A3 plus has a what? Has a subscript S2. So we will raise it to the power 2 as well. So we have to multiply the S with 2 and raise to the power 2. Similarly, S is multiplied by 3 and raised to the power 3. So finally, we got 108 multiplied by S raised to the power 5. Do we know the value of KSP? Yes, it is given in the question. It is 1.1 into 10 to the power minus 23. Put this value in your KSP place, and finally, you will get your S. On rearranging this equation, we will get S raised to the power 5. So 1.1 into 10 to the power minus 23 divided by 108, and that is approximately equals to 1 into 10 to the power minus 25. Finally, if you just take this 5 on the right hand side, so 1 into 10 to the power minus 25 will be raised to the power 1 by 5, and that calculation will give you the solubility as 1 into 10 to the power minus 5. So finally, we can summarize all of this that we have dealt so far. So we in the start we saw that the solubility equilibrium. So sparingly soluble salt, upon dissolution in the solvent, they establish a dynamic equilibrium state where the undissolved part and the dissolved part are in the state of dynamic equilibrium, and it creates a saturated solution. Second thing we saw that is the solubility product, which is nothing but the ions concentration multiplied, and each individual ion is raised to the power which is equals to their stoichiometric coefficient. Then we saw what are the factors that affect the solubility. So the most important factor is temperature, which is mentioned here, and then we have lattice enthalpy, solvation enthalpy, and the solvent effect. Further, if you want to dissolve a salt in a given solvent, then your magnitude of solvation enthalpy must be greater than lattice enthalpy. We saw that in the discussion of the polar and non-polar solvent, right? So if you are releasing more energy, that means as compared to the energy which is involved in breaking the lattice, then and then only your salt will be soluble. Further, if you want to predict the precipitation, it's very easier. If your Q is greater than Ksp, precipitation will occur. If it is less than Ksp, then precipitation will not occur. Instead of that, more salt will be getting dissolved into the solvent. And third, if both are equal, then the equilibrium is attained and no further change is seen in the concentration of the ionic species. So there is a state of dynamic equilibrium. So this was all for today's class. Thank you for joining the session. I hope you enjoyed it.